Hello friends, welcome to this YouTube channel. Today we are going to solve a couple of numerical problems on electrical circuits containing both dependent and independent energy sources using node voltage analysis technique. Node voltage analysis method is suitable for circuits having many parallel connected elements, current sources, or super nodes. Using this method, we can determine branch currents, voltage drop across a particular circuit element, or power consumed by an element. When circuits containing dependent sources are analyzed, initially a dependent source is treated as an independent source. Later, constraining equation is written to include the effect of dependency. Problem number 1. In the network shown, we have to determine Vx. In this circuit, we find one dependent current source and one independent voltage source. At first, we shall treat the dependent source as independent source. Later, we shall write one constant equation to include dependency. Let us mark the essential nodes as 1 and 2. Associated node voltages are V1 and V2 respectively. We are selecting node 2 as reference node. Therefore, V2 equals to 0. We shall write equations taking V1 as variable. Here V1 equals to Vx. Let the current flowing through 20 ohm resistor be I. Here I equals to Vx by 20. At node 1, we observe that 5Ix and Ix currents are entering the node, whereas I current leaves the node. Therefore, applying Kirchhoff's current law, we get 5Ix plus Ix equals to I. Using expression for I, we get Vx by 20. Rearranging this equation, we get Vx equals to 120 times Ix. Now we shall write the constant equation. From rightmost branch, we get Ix equals to 500 minus Vx divided by 5. From above equations, we get Vx equals to 480 volts. Problem number 2. We have to determine the current flowing through the 5 ohm resistor. Let us first mark the essential nodes as 1 and 2. Associated node voltages are V1 and V2. We are selecting the second node as reference node. Therefore, V2 equals to 0. We shall write equations taking V1 as variable. From the middle branch, we get our constant equation V1 minus Vx equals to 4. Let us assume that currents at node 1 are leaving the node. Now, applying Kirchhoff's current law at node 1, we get V1 minus 3Vx divided by 5 plus V1 minus 4 divided by 2 plus 2 equals to 0. By simplifying this equation, we get 7V1 minus 6Vx equals to 0. We have two unknowns V1 and Vx, and we have obtained two equations. By solving them, we get V1 equals to minus 24 volts and Vx equals to minus 28 volts. Now we shall determine current flowing through the 5 ohm resistor. I 5 ohm equals to V1 minus 3Vx divided by 5. Using values, we get minus 24 minus 3 into minus 28 divided by 5. That gives us 12 ampere. Problem number 3. We have to determine the voltage drop across 5 ohm resistor. Let us first redraw the circuit and mark the essential nodes as 1 and 2. We are selecting the second node as reference node. Therefore, associated voltage V2 equals to 0. We shall write equations taking V1, the associated voltage of node 1, as variable. From rightmost branch, we get our constant equation I1 equals to V1 minus 50 divided by 30. Applying Kirchhoff's current law at node 1, we get V1 by 5 plus I1 plus V1 plus 30 times I1 divided by 10 equals to 2. Using the expression of I1, we get V1 equals to 20 volts. We observe that voltage drop across 5 ohm resistor is V1, that is equal to 20 volts. Problem number 4. In the network shown, we have to determine the value of Vx. Let us first redraw the circuit and mark the essential nodes as 1 and 2. Associated voltages are V1 and V2 respectively. Let us select the second node as reference node. Therefore, V2 equals to 0. We shall write equations taking V1 as variable. Here we observe that V1 equals to Vx. Now we shall write our constant equation Iy equals to V1 by 10. Applying Kirchhoff's current law at node 1, we get V1 minus 2Vx divided by 50 plus V1 by 10 plus V1 by 5 equals to 5 plus 2 Iy. Using expression of Iy, we get 5 plus V1 by 5. By rearranging this equation, we get 6V1 minus 2Vx equals to 250. Since V1 equals to Vx, we get 6Vx minus 2Vx equals to 250. Therefore, Vx equals to 250 divided by 4, that gives us 62.5 volts. Problem number 5. We have to determine Vx, the voltage drop across 2 ohm resistor. Let us first redraw the circuit and mark the essential nodes as 1 and 2. Associated voltages are V1 and V2 respectively. Let us select the second node as reference node. Therefore, V2 equals to 0. From the leftmost branch, we get our constant equation Iy equals to 4 minus V1 divided by 1. That gives us 4 minus V1. Applying Kirchhoff's current law at node 1, we get V1 minus 8 divided by 2 plus V1 by 1 equals to 4 times Iy plus Iy. Using expression for Iy, we get 5 times 4 minus V1. By rearranging this equation, we get 13V1 equals to 48, or V1 equals to 48 by 13 volts. Inspecting the rightmost branch, we get Vx equals to V1 minus 8. Using value of V1, we get Vx equals to minus 56 by 13, that is equal to minus 4.3077 volts. So today we have solved a couple of numerical problems on electrical circuits containing both dependent and independent energy sources using node voltage analysis technique. Using this method, we can determine branch currents, voltage drop across a particular circuit element, or power consumed by an element. When circuits containing dependent sources are analyzed, initially a dependent source is treated as an independent source. Later, constraining equation is written to include the effect of dependency. Hope this lecture has been useful for you. If you have any suggestion or question, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.